will be Scott Kelly. He is the Southwest Regional Sales Manager for APM Permaform.
Good afternoon, everybody, and thank you for coming in. The title of the presentation is the Rehabilitation and Subsequent Stress Strain Testing, but I didn't really tell you, y'all might have figured we fixed something, but didn't really know what it was. So I'm here to relieve that tension right now and tell you we're here to talk about culverts. One in fact that we did 6 or 7 years ago in 2010 out on SR 16. It's located about an hour southwest of Jacksonville, I would say, not too far from here. Back in '08, Tropical Storm Faye cruised across Florida and in an amount of 10 days or so dropped in excess of 28 inches of rain. And that kind of rain event will expose hidden defects or underlying defects you have in your storm drain system. This is a photograph of the two-lane rural highway that is SR 16, heavily traveled. The flag you see there on the left is top dead center of the crown of the pipe. And what is extraordinary about this pipe in particular is that it is less than a foot of cover over the crown of this pipe. They discovered the large void, as the story goes. A state patrol officer had stopped over the culvert and was evidently writing someone a driving award, and his car suddenly broke through the pavement and actually landed just right on top of the culvert. So at that time, further investigations were done, and they determined they had some large voids that were caused by defects in the invert of this culvert that were piping soils from the upper levels and removing them through the flow in the stream there. So FDOT did a thorough investigation. They examined different means of rehabilitating this pipe and or digging it up and replacing it. And ultimately, to just cut the short to the chase, they selected to use a fine aggregate composite concrete, or FACC, lining to stabilize these defects in the pipe and prevent that soil piping issue that was going on and causing destability in the soil envelope around this structure. The main reasons and attributes they chose this is we were minimally effective, minimally impacted the traffic flow patterns on this highway. We didn't even have to do a lane closure, as a matter of fact. We provided a long-term, a long life, service life with this type of technology, and it's a fully structural independent pipe within the existing pipe. So in considering these types of systems, and there are competitive systems on the market, you want to make sure that the manufacturer can provide you with an engineering design guide that gives you in-depth situational conditions, how to deal with those situations in the environment of the pipe itself. And also you want to give them input on engineering calculations to deal with various concerns that are present in that pipe in situ condition. So in designing the minimum lining thickness on these liners, we want to look at certain characteristics that are in the on-site conditions. We want to look at the pipe size, obviously, and the construction. Is it a corrugated metal pipe? Is it a multi-plate? Is it a reinforced concrete pipe? What is the shape of that pipe? And we also want to analyze what its current geometry is. It could be deformed. We want to look at the pipe condition, the depth to the crown, obviously, pavement type. Is it an asphalt pavement or a concrete pavement that distributes live load differently? What kind of soil type do we have encasing this pipe? We also want to look at the water table, corrugation pattern, hydraulic capacity. Do we have any left, or are we at the tipping point? And then also load requirements. What is the load? If it is a paved surface, what is it rated for? And then any future loads that could possibly be induced on the pipe down the road. So in determining the required minimum wall thickness, we want to see, is there any long-term structural value in the host pipe structure? With corrugated metal pipes, typically we'll use a fully deteriorated design model. So we're not assigning any structural value to that pipe. Even though the pipe still may be functioning in quite a deteriorated state, like the picture you see on your left there, they still hold shape and function for the most part. There's shape holding, in other words. In a concrete pipe or a brick structure, we will actually, depending on the deteriorated state of that structure, assign a structural value to that structure. So how does the lining system perform within the host structure? Is it going to perform as an unbonded or a bonded condition between the liner and host pipe interface? So in an unbonded state, it's going to be a compound beam, which obviously puts more stress on that interface. A bonded configuration is going to be in composite beam and is going to be more stable with less stress between that interface. What loads, if any, are likely to come onto the lining after installation? So obviously we want to look at the cover depth of that pipe and also the diameter or the span. We also want to look at the phreatic surface of the water table because that can also induce pressures on the pipe. And we want to look at and analyze any potential live loads that could come onto the pipe. So lastly, we want, and probably the most important thing is we want to determine what the likely load response is going to be of this structure. Is it going to act as a simple beam in bending, or is it going to react more like an arch structure and be in thrust? And we found that if we can keep our designs in that thrust or composite stress there, we can exponentially raise our safety factors while minimizing the lining thickness and make the lining more economical. So looking at different FACC lining materials, we want to look at the FAC Mix Design's physical properties, and these are properties that can be published on paper, but they're white and black. We don't know necessarily what or how the material is going to perform in the structure itself. We also want to look at the application methodology. Depending on how you install that material in the host pipe, you can harm or improve those physical properties that you have published on that material. Obviously, we want to look again at the existing soil structure interaction system, and that's how the existing structure is behaving with the soil envelope that it's in. And obviously determining the loads that will be applied after lining takes place. So we're not really designing a lining inside of a pipe, even those are the typically thin profile. We're designing a self-independent pipe within a pipe. So on the soil structure interaction, I'm going to read you a quick quote here. The real behavior of structures in contact with ground involves an interactive process beginning with a state of balance after a period of adjustment of stresses and strains within the structure and within the ground influenced by the structure. A buried pipe, when installed by open trench, is going to come upon its greatest stress right after burial. And after a period of adjustment, those stresses should balance out and you should reach a state of static equilibrium. So some of the physical characteristics that are important in the FACC lining, we want to look at the modulus elasticity, the flexural strength, the thin shell toughness, and I'm going to go into that in just a minute, permeability, freeze-thaw performance, the thixotropic nature of the material, and you want to have an internal crystalline membrane technology. We are talking about a monolithic concrete structure here, so any hairline cracks that could develop over time, we want to have a technology present that's able to autogeneously heal those cracks with the presence of water. Looking at these physical properties, we see in this graph, you can have a material with very similar modulus elasticity, but they behave completely different up to the point of rupture or modulus of rupture. What we see in a brittle material is a high strength grain, but then once you hit to the modulus of rupture point, you have a complete strength loss. What we want is a material that has some ductility that's able to absorb that energy, and that's how we respond to toughness. That thin shell toughness is the ability to absorb energy up to that point of rupture. That's a better indication of how that pipe is going to function or how that lining is going to function in the ground with a semi-rigid host pipe configuration or in a reinforced concrete pipe situation. So in analyzing the corrugation profiles in this particular pipe here, we had a 2x6 bolted multiplate. The way we calculate the minimum lining thickness is measured off the crest of the corrugation. The material that we use to fill in that corrugation, all of that material in the valleys adds to the structural integrity of the pipe lining, but we don't consider it in our engineering calculations. It's all based on the peak measured inward. Also, any penetrations in the pipe, like bolts, we have to have a minimum of a 1/2 inch of cover, and that's going to prevent any star cracking that could occur directly over the tops of those bolts. So just to touch on integrated structures and materials design. This is a concept where we take 3 basic design elements and they all convene to assign what is our material properties installed. So in the upper right-hand corner, you see the structural mechanics, and that's all the things we talked about with the in situ structure and the condition of the structure and the depth of the structure and all of that. In the bottom triangle, we're looking at material properties, and that's all our physical properties we just went through. And then the installation mechanics. Pending the procedure that's used when you install the materials, you can enhance or harm the final physical properties that you have in the structure. So when all of those work together in concert, really your true performance is going to be determined how those all 3 integrate together. So to cover this job real quickly, this is the 13-foot diameter pipe with minimal cover. FDOT wanted to maintain the creek flow through this pipe, so what we did is cofferdam and use an HDPE pipe to segregate the flow within this pipe. And here you see another shot of it. So we were able to work within the confines of the pipe without having the influence of the flow. We also wanted to add some channelization devices so that we put wing walls and approach slabs and exit slabs on the structure to help channelize the water through the structure. To repair the invert, where the invert had corroded or eroded, in a lot of cases, we used a flowable 12,000 PSI fill material that goes in and technical term is nooks and crannies. It fills all those annuluses beneath the pipe where water is likely to flow outside the conduit. We want to ensure that we get that pipe on the soil envelope complete around the structure so we don't have water migration. We have all the water moving inside the conduit. Any water that's allowed to move outside that conduit can potentially cause you the same problems that they had initially with this structure. The equipment that we use for this process is modular, and it's a small footprint, so we rarely impact normal traffic flows and things like that, or we minimally influence those things. In pipes that are greater than 10 feet in diameter, we typically will hand spray the material. This is because, I should back up. We typically will use a centrifugal casting process with this. We have a spinner head that's air operated. We did a demo out front this morning. The material is pumped through a spin head that's spinning in excess of 5,000 to 6,000 RPMs, and the material is distributed against the host structure, which compacts and impacts that material against the host structure. In large diameter cases, our fiber package will segregate from the material in flight if it's too far. So in these structures, we found we can create more density using a low pressure shotcrete application method. So the material's gunned on in layers. We build it up and then finish it by hand. This is what it looked like on day 1 after the structure was completed in 2010. And there's a shot of the complete, and you can really see the shallowness of this culvert and why it is truly extraordinary. So in January of 2016, I happened to be in the neighborhood and said, well, you know, I'll drive by this culvert and go walk through and see how she's looking. And I found it to be in just impeccable condition. This is shots taken on that day. This is a shot of the crown that's directly under the shallowest part of the road. Really in terrific condition and performing exactly as it was designed. And this, I remind you, is a 2-inch thick lining of PL 8000 FACC material. It was performing so well, we had an idea we'd like to understand better how live load stresses influence our lining systems. So we found a company up in Maryland called Resonances. Anyway, they were able to put high gain sensors in the crown of the pipe. We positioned those sensors such that they were right under the wheel loads in the east and westbound lanes of SR16. And they're comprised of a full pad that's literally glued to the crown, and then the device just off of that, at the end of the wire, is a transmitter, and that transmits the data to a data collector, which then cellularly transmits the data to the computers. In order to put a live load on this pipe, we employed a semi-flatbed tractor trailer loaded with sod that weighed 83,600 or 260 pounds. We rolled, there's the truck, and you see the flag that I mentioned before is top dead center. We stopped the drivetrain and the trailer wheels directly over the pipe. In addition to, we rolled the pipe in east and west directions at 3 miles an hour to get an idea of how load transfer was occurring on the pipe. When we stopped the truck dead over the pipe, we held it there for 45 seconds so that we could monitor the strain that was induced on the pipe. And I know this is difficult for y'all to really make out, so I'm just going to have to interpolate it for you. What we found was a strain increase that was completely negligible. In fact, the maximum reading was 6 microstrains. These high-gain sensors were accurate up to 2 microstrains. So we had very little stress or strain increase on this pipe when it was loaded. This is at 3 miles an hour, east and westbound, and then dead stop on top. And you can see the spans there from the arrows that are depicted beneath the graph. This was a moment of time that the trailer wheels were positioned dead over the top of the pipe. And there again, very minimal strain on this pipe. So in summary, you want to make sure you select a FAC lining system that can deliver the performance required by the design of the proposed liner. And really, experience is what you're looking for, proven experience in the field. You want to confirm the existing pipe structure is in static equilibrium in its current geometry, include appropriate repairs to correct voids. Determine the dead loads and live loads likely to come onto the pipe or the structure system. Load response, is it going to be in simple beam or is it going to be in thrust? And then you want to have third-party evaluation of the materials that you're going to use. Lastly, the strain testing that we did proved that this lining system and our design methods are performing well within the design capabilities of the liner.
How long does it take to do process?
How long does it take? Depending on ambient temperatures. Down here in the summertime, we can do a single pass through a culvert and repeat that process in as little as 2 hours. We get about 4,000 PSI in 24 hours, so it's a pretty high strength gain material. Another advantage is if you have a weather event while we're in the process, we have to do obviously bypass pumping in many cases are like this. If we have a weather event, we can simply just pull out of the structure, let the weather event pass, let the water drop, and then we go right back in. Worst case scenario is we were doing a culvert up in New Jersey and a hurricane came through and we had to pull out with 3 hours cure time on the liner and ultimately caused no damage. So it cures rapidly.
You're creating pipe within the pipe, and obviously you're not relying on the structure of the corrugated pipe. So basically this is a non-reinforced pipe. How big is the pipe that you can go up to with non-reinforced? The second question is, if you are non-reinforced pipe, how you ensure that the load, I know that you have to do the testing for the strain rate. How do you ensure that the compressions and all this pipe does not collapse in the future?
Well, your first question was in regards to non-reinforced pipe, but this is actually a reinforced pipe. We reinforce the material through a complex microfiber package, as well as mineral fibers and nanofibers. So it is a fiber reinforced material. Your second question is we have a detailed methodology of engineering to determine what our lining systems can carry load-wise. Two, we look at the cover depth and we know what kind of live loads we can anticipate on those structures. We have means and methods of analyzing all of those, not beyond just the third-party testing where we're in a lab telling you what the physical properties are. We've actually been in the field and had these structures in service now for over 15 years.
Your presentation was corrugated metal pipe. With plastic pipe, concrete pipe, what type of pipe do you rehabilitate the most frequently?
Corrugated metal, without a doubt, and I think it's just a economy of scale deal. There's just so much of it out there that's in excess of 30 years old and looks pretty much like the pictures I showed you. They're just gone. But shape holding is still functioning, so we can go in and if we can maintain that soil structure interface, then we can preserve it for the foreseeable future.
Okay, just to follow up to the question before that one, you've got fibers in the mix, but do you ever add a layer of mesh or reinforcing cage inside the structure?
We have done that in the past. It's not done so frequently now that we know more about the in situ performance and how we do perform in these type situations. This particular structure had no mesh. We have done it in the past.
Could you give us some idea about the cost?
I'll try to give you an idea. Depending on the density in the area, this is a technology that does well in urban environments where you have a lot of restoration cost or possibly various utilities that prevent you from digging up a pipe. In most conditions, we can be anywhere from 30 to 50% cheaper than dig and replace. Now, obviously, that doesn't include a 3-foot pipe that's out on a simple paved road that's easily accessed and can be dug and replaced. We won't compete with that. We don't look for those situations. We're looking for pipes that are going to be difficult, arduous to dig up and replace and have plenty of hydraulic capacity, and we can repair those very efficiently and cost effectively.
Are there limitations on non-circular pipes or not very circular?
Not really limitations. We really go in and examine the existing geometry, and we'll look at the arch rise parameter and determine, and that'll influence our minimum lining thickness. So we can work around some pretty gravely distorted shapes. But there can be limitations to anything. Once you get a full catastrophic cave-in, typically you're going to have to go in and dig that pipe up. We have had instances before where pipes mysteriously get placed under buildings, kind of like I left culvert out of the title, and you can't dig them up, so it's not an option. In those cases, you almost have to treat it like a tunneling expedition. You go in and you take out small sections, and then we'll use a multi-plate liner to reestablish the structural safety of the structure, and then you just segmentally go through that section until you can then go back in and line it with the composite material.
Is there a certain surface profile or prep that's needed or a guideline for that prior to application?
We go in and high pressure water blast, and we take out any debris. We'll go in, and part of the preparation of this is to repair any defects, misaligned joints, holes in the pipes, things that are going to upset the continuity of our lining as we pull through the pipe. We also acoustically sound the pipe to determine if we have any voids outside it. So all of those things are addressed by hand as part of the preparation before we go in and actually spin the liner in the pipe. Just pressure washing, though, is typically enough. We just want to get all the unbonded or loose material off the surface.
Is that dry then first?
No, we actually prefer wet. It assists in hydration control.
Steel reinforced like a box culvert bridge, not an issue. Because I know a lot of issues here in Florida. We have issues with scaling, and that seems to sometimes present a problem. They go in with normal shotcrete. Overhead seems to be a problem. You're saying overhead application doesn't seem to be a problem. You mentioned that you've used supplemental reinforcement, welded wire fabric. So if you have some areas where you have exposed steel, you don't have any issues with that. You can get up probably a couple inch, or do you prefer to stay at the half-inch overlay?
No,
in other words, there's different scenarios that
Sure.
happen with some of these square box culvert bridges.
Yep.
With scaling issues that need to be built back up and do have exposed steel.
They do, and their standards, when you have steel, you have to have a minimum amount of cover over that steel. So we're bound in our designs in what we do, what's in code and what we have to do. So anytime I'm doing a more conventional concrete repair or rehabilitation system, like in a box culvert or something, I employ standard practices to do that. Even though we're using a highly engineered material to reinstate the dimensions of that structure, we still have to follow guidelines, exposing steel, sandblasting steel, maybe epoxy coating that steel. I want to tie that material to the structure mechanically and not just rely on a box is different than a circle. We don't have a true bonded interface there. We have to rely on a mechanical interface to make sure that our inlay material stays put. And then our preparation is totally different. We can just go in and water blast anything that's scaling. We have to actually chip down and get the sound concrete that we can bond to and effectively rely on to reinstate the structural integrity. That's not to say, though, and a bad habit I've seen here in Florida is assigning no structural integrity to an existing box culvert because it's lost 2 inches. It's not just dirt, it's good concrete, use it. We don't have to put 6 inches on the inside of that box. We can do it probably with 2 or 3. As long as we get that cover over the steel, we can protect it. This material tested with chloride ion permeability at below 50, a 44. That gives you an idea of the water tightness we can achieve with spin casting techniques, and that's part of the application process. No, sir. We do arched, ellipticals, teardrops, just about any shape that you can think of. The only deciding factor in that is if we have an arch pipe, let's say, we have to gauge and measure our minimum lining thickness from the points that are most distal to the spinner head. Those distal areas will gain thickness slower than the surfaces that are more proximal to the spin head. So we just want to ensure that we get the minimum lining thickness on the haunches, let's say, of an arch pipe or an elliptical pipe. Well, depending on what the span is and what the rise is and the depth of cover and how the loads are influenced in that structure, all of that comes into play. So a circular pipe could function just like an arch pipe or vice versa, depending on those variables.
So based on your strain gauge measurements, were you able to resolve a load rating for the structure, or are you entirely relying on the load test?
Well, we really just wanted to establish a benchmark or have a known point of time. I might note, we monitored those strain gauges for a month after those individual tests were done. So we really just wanted to have a marker in time where we had a known load roll across the culvert and then record what influence it had on the structure. So in doing that, we just really wanted to learn more about how live loads were influencing the performance of our structures, gain our private knowledge on what we're doing right, and possibly learn something if we were doing something wrong. But all indications are the material is performing much better than what we would have expected to see in a structure with less than a foot of cover on a highway rolling these types of loads across it, without doubt.
Well, I guess ultimately as a owner, we have to provide a load rating back to FHWA as part of our annual submittal. And so I'm curious what Florida's providing for this structure. Are they using an assigned load rating, or did they actually calculate something?
Well, Bob Savoy told me on this particular road, he's a District 2 engineer in Jacksonville, that this road is actually rated for a maximum load of 200,000 pounds. So it met those requirements without leaks. Obviously, we couldn't arrange for a 200,000 pound load to come rolling down the highway, but it evidently happens because of the military-based traffic uses 16 frequently. And this culvert's obviously seen some loads similar to that. Or we suspect it has. Oh, it has. I'll just tell you it has. We're at the time. Good. Well, typically, I'll answer this quickly. In a corrugated configuration, Manning's End coefficient is going to be about a 0.023 on day one. Our average is going to be a 0.014 to 0.016. So we'll have a minimal decrease in cross-sectional diameter, but we typically will either break even or improve the hydraulic performance of the pipe just in the reduction in Manning's End. That's not always a good thing. A lot of people are concerned about increasing flow and doing downstream damage because of it. So we can incorporate obstructions in the liner and the invert to slow that down if needed. Lots of different things we can do. But hydraulic performance is typically improved, or at least we maintain what you have. We can also go in the inverts and up to the spring line, we can go in and hand finish to improve that Manning's End. If you're, say, on your hydraulic bubble there and maybe needed a little extra capacity, we can smooth that finish out. We could also install a slicker surface, like an epoxy type coating over the top of it to improve that. Different things we can do just to maintain the functionality of the pipe. Thank y'all.
The preceding was produced by the National Center for Pavement Preservation. More information can be found on the web at pavementpreservation.org. Additional support provided by Michigan State University.